Okay, so I thought it'd be a good idea for me to document me trying to learn something completely um out of out of my league, right? This is a partial differential equation, and right now I'm currently in ordinary differential equations, and I'm a sophomore, right? So this is definitely out of my league. I mean, to actually do these proficiently, to actually do partial differential equations proficiently, I believe it's a graduate level class, right? Or at least it would be one of the last classes you take as a senior in pure mathematics, right? I don't think engineers would even cover really doing hardcore partial differential equations. And now, truthfully, I'm only going to find a general solution, so I don't even have boundary conditions or initial conditions, and that's because if I was to add that stuff in, this would be really hard, right? But I'm just going to try my best to solve this. Okay. Okay, so maybe I should start by changing the notation, or not changing the notation, but I should maybe write this in a form that looks easier for me and just indicate something. So okay, so we see that u is a derivative taken to t, and u is also a derivative taken to x. Well, u is a function, and it can be taken to t and x when you're talking about derivatives. So that can tell me that u is a function of x and t. Thus, we can write it as x is a function of x multiplied by t is a function of t. Right? We could write this, and this is just a way to describe it. So then if that's true, I could maybe say that ut, and let me just write it as du dt, just for familiar sakes. I could say that this is the same thing as something like, um, it would be like what? It would be t prime t, so time t prime t times x of x, and yeah, I know I'm kind of jumping notations here, but like I'm doing it purely just to try to be familiar and make this as easy as possible. And whatever comes to my mind, right, as I'm learning something, that's how I'm going to try to do it. So I'm just going to rewrite this as t prime and x. All right, okay. And then I could maybe say that u xx, I'll describe this as d u dx squared. I could write this, I guess, as x double prime x multiplied by t of t. And then I could write this, of course, as x double prime t. And yeah, I know I'm writing big T here and then little t here, and this, yeah, this should like all these T's should be big T's, right? But I mean, sometimes I just randomly write small t. 'Cause I'm so used to writing. Okay, so this is useful. Now I can rewrite my differential equation, and I should just say that alpha squared is a constant, right? So we know that alpha squared is a constant. I mean, okay, so let's write this as t prime x, and that is equal to alpha squared x double prime t. Okay, so if this is true, maybe I can use a separation of variables. If I use a separation of variables, I just want all the t's on one side, all the x's on another side. So I write it like t prime t is equal to alpha squared x double prime divided by x, right? Okay, so that works. I mean, that's true. Like, well, how useful is this, right? I mean, what can we really do? Like, I guess, like what you could do is you try to do it like you do in ordinary differential equations, and you start trying to integrate. But since I did read the book and I have an idea of how to do this, the trick is, it's not really a trick, it's kind of you have to do this, is you set it equal to some constant. So this is just some unknown constant, but it's saying that these two things here are equal to some constant. Okay, and if that's true, if they're both equal to some constant, then we can take them individually, right? We can take them individually and write it as two ordinary differential equations, right? So we could say t prime t is equal to k, and alpha squared x double prime divided by x is equal to k. Okay, so that's kind of useful. That's now helpful. And if that's true, then I guess I could actually start doing what I want to do, right? Okay, so now let me just write these in green because this is going to be the next big step. So I'll write it as t prime is equal to, I'm going to do minus k t. That's equal to 0. So originally I had a one differential equation, and it was, I had two independent variables. I made it into separable with two independent variables. I mean, well, separable. Oh, damn it. Separable here, but then now I have two ordinary differential equations with only, obviously one independent variable. And they're both homogeneous, which is pretty nice. I guess I could write this as x double prime is equal to minus k, no, k alpha squared x. And of course that is equal to 0. Okay, so this is now this looks familiar. This area looks familiar. Okay, and real quick before I do anything, this right here, what I could have done earlier is I could have the alpha squared over here, right? All I had to do is just divide it instead of keeping it on the side. So I'm just gonna rearrange everything now, just because this looks kind of clunky. I'd rather have it here. So like this is allowed because right here all I had to do is change it. So I could write this as t prime minus alpha squared k t is equal to 0, and x double prime minus, yeah, kx is equal to 0. Okay, now these are okay, this is a linear first order differential equation. I know how to solve this. And this is a second order linear differential equation. I know how to solve this. I'm going to be transparent. Yeah, there's one more thing I needed to do. Hopefully, maybe you know it, but I didn't know it at the time. It's actually really important. Okay, so it's t prime minus, well, we're going to turn it into plus a squared lambda squared t is equal to 0. This will be x double prime plus lambda squared x. Yeah, it's equal to 0. Now, why am I doing this? Pretty important reason. Okay, lambda squared is equal to negative. Okay. So what we're trying to indicate here is that, okay, now like the reason why you need to actually do this is because if I was to give you boundary conditions, and I'm actually going to do that now, so boundary condition, and I'm only going to give one, and this is like kind of necessary, and this is just logical sense what I'm about to do. It's just saying that like time goes on forever, right? Like this would kind of indicate like what I had here. If I solved it and I got a solution, it wouldn't really indicate that time goes on forever, right? That the solution would be true for time going on forever. So you do need to rewrite your constant here to actually create a correct or physically correct solution, right? Or at least a logically correct solution. But again, I'm just learning, right? So it's good to be transparent and show you guys that there's going to be a lot of downfalls here. Okay, well, if that's all true, and then now I'm going to start solving these. So I rewrote it like 4 different ways, just start being able to solve it. Right? That's, I guess, what this class is really about, learning how to rewrite things into something that you can see. So if I use the method where I just call the derivatives of a order a polynomial of a degree, right? Okay, this is m plus a. Yes, my a's have just turned into, I mean, my alphas have turned into a's. Yeah. M squared plus lambda squared is equal to 0. Okay, so then we could see that m is equal to, well, it's going to be equal to negative a squared lambda squared, and then we would see that, okay, m squared, why did I do that, is equal to negative lambda, and, well, what does that mean? Okay, so it's 0 plus or minus I lambda. Okay, so recall the general form would be x is equal to c1 sine lambda. Sine lambda what? Sine lambda x. And c2 cosine lambda x. Okay. So that's true. Okay. What am I? Okay, this one. Okay, well this is a lot easier. Where it's t. T is going to be equal to. Okay, I'm gonna pick c3, right? And it'd be e to the negative alpha squared. Not k squared, lambda squared. Lambda squared. Okay. So I got a fundamental solution here and a fundamental solution here. So, okay, remember how I separated things and I turned it into two different things? Well, I'm going to have to go back now and combine these two things by multiplying them together. Okay. So if I multiply them together, I get, well, I could say that u, well, right, u, where u is a function of both of these variables. And then that is going to be equal to c3 e to the negative a squared lambda squared parenthesis c1 sine lambda x plus c2 cosine lambda x. Okay, so that's actually my answer. It's a lot of work for this answer at the end. Okay, yeah, well, I just solved my first partial differential equation, and I have really, honestly, no idea what this even means, right? And let me just check if I got it correct. Okay, so I did mess up somewhere, and hopefully you caught it. You should have caught it right here, and catch it right here. So we'll write this error in blue. So the error is the fact that I didn't put the extra t here, which is it's kind of a bummer that I messed that part up. I mean, that part was should have not been that hard. I'll do it in red. T. Okay, so then this becomes t. Okay, yeah. The reason why I forgot is because I forgot it, but the reason why, I mean, I checked the book, and let's not forget that this is like a Cartesian very general form. It goes c1 e to the mx plus dot dot dot, right? And that's what happens when we solve a differential equation with a real root, right? You get this solution, this general solution, and yeah, and that's if y is a function of x, right? That's if y is a function of x. You need to factor in that there's always x here, right? And in this case, t t was our dependent variable. Therefore, it has a God, partial differential equation's hard, but yeah, there's a t here, so there must be a t here, right? Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up the algorithm.